Okay, so for question 2, we are looking at the Dijkstra algorithm. For the Dijkstra algorithm, aside from the graph representation, the other data structure that we maintain is a priority queue. For the priority queue, it maps each of the node or vertex to the distance of the vertex from the start. And at initialization, or like at instantiation, um, aside from S, which has the initial value of 0 being the starting node, all the other nodes have the initial values of positive and negative. And these values would get updated along the way. The other thing to know about priority queue is that we pop off a node from the priority queue when it has the smallest distance value. That means that it is closest to the start. And once we pop a node off, this means that we are receiving the node. So the values of the node that is connected to that node will be updated. Like they will have the new distances reflected in the priority queue. Like for working purposes, we also keep a table that has a 3 columns, vertices, distance to, and edge to. The distance to will help us to keep track of the distance of the node from the start, and edge to will record the preceding vertex from the node that we are currently at. Okay, so without further ado, let's see how everything works in real time. So as mentioned, S will be pop off first since it has the smallest distance value, okay, or it's just a start itself. Okay, and after that, since A is the only node that's connected to the start, only the value of A gets updated to 1. And again, it will be popped off since it is the closest to the start. So it will have distance of 1 and edge 2 will be S. And at node A, we are able to update the distance values of node E, D, and B. E will have the value of 2, D will have the value of 4, while E will have the value of 9. To clarify here, like the 2, 4, 9 comes from 1 plus 8, 1 plus 3, and 1 plus 1. Yeah. Okay, and at this stage, B will be the one that's closest to the start, so it gets popped off. And it gets updated to distance will be 2, preceding vertex will be A. And at B, the only node connected to B will be C. So C gets updated to 3. Again, it is still the smallest value closest to the start. So C gets popped off and updated in our table. Okay, so we know that it has kind of like reached the end from a certain direction in the graph, but we don't need to do anything. We just like go back to our priority queue to see which is the node that has to be popped off next. So at this point, D will be the one that's popped off, and with a distance of 4 and the preceding vertex of A. And at D, the only node that's connected to D will be G. So the value of G gets updated to 6, being 1 plus 3 plus 2, right? And yeah, G is still the smallest when compared to E, so G gets popped off. And yeah, congratulations, we have already reached the goal. So that means that we have done traversing the graph. So we can use a table to help us to backtrack our path. So from G, it goes back to D, from D it goes back to A, from A it goes back to S. So our full Dijkstra path will be S, A, D, G. Okay, for part B, we are looking at an advanced version of the Dijkstra algorithm, that is the A-star algorithm. For the A-star algorithm, it is more advanced because it will be able to help us get to the goal in much shorter time, because it will avoid choosing the path that leads to a terminal node that is not the goal. Like for example, in Dijkstra, we will lead to a dead end of the C node, and C is not the goal. So we kind of like wasted the whole traversal from S, A, B, C. So that is what A star helps to prevent. And A star is able to do that because of its different way of calculating the distance. Like, as you can see here in orange, like the distance value is not only the distance from the start, but it also includes a heuristics term. And the heuristic value are essentially an estimation of like the distance from the node to the goal. So as we can see from the graph, like since node C is so far off from the goal, like totally different direction, it will have the highest heuristic value. Whereas all the other nodes that's kind of like closer to the goal, it will have a much lower heuristic value. Like for example, E has a heuristic value of 1, whereas T has a heuristic value of 2. And this updated distance value will be the one that we used to update our priority queue. However, in the table itself, we will still keep to the distance value from the start, like without the heuristic term. I hope that things will get clearer as we work through the entire problem, which is now. Yeah, let's start. Okay, let's pop off node as, and then add as will be update. We'll be able to update the distance value of A, and including the heuristic value, the distance value of A would now be 1 plus 5, which is 6. And A will be pop off since it is still the one node closest to the start. Okay, yeah, as mentioned, in the table, we will still keep track of the distance from the start without the heuristic value. So A will take the value of 1 under these two, and the preceding vertex will be S. Okay, and at A, we will be able to update the values of B, D, and E. B will now be 1 plus 1 plus 6, totals up to 8, and D will be 1 plus 3 to 2, totals up to 6. Oops, I forgot to add that in. Okay, and E will have the value of 1 plus 8 plus 1, so that is 10. As we can see here, like rather than in Dijkstra, which like at this stage it pops off B, but now we are able to pop off D rather than B. Yeah, D will have the distance value of 4 from the start, and preceding vertex will be 8. Okay, and at D, we are directly able to update the value of our goal, which is 1 plus 3 plus 2 plus 0, that is 6. And yeah, we are able to pop it off too. So we have already reached the goal node, and our traversal has come to an end. So as you can see here, like A-star really help us to prevent traversing the lane of S, A, B, C and lead to the dead end of C. That is not our goal. So by doing that, it really helps to, like it really helps us to get to the goal in much shorter time. Like even though the shortest path is still the same, we shouldn't the shortest path that return from A star should not be different at all, because like it is still the same distance value in essence without the heuristics. Yeah, so as we can see, like just like backtracking from our table here, the shortest path is still S, A, D, and G. Okay, for part C, we'll be looking at the runtime of Dijkstra and A star, and we will also be looking at the space requirement for the algorithms. Let's start with runtime. Our cost model would be the operations of the priority queue. In the case of Dijkstra, we know that at the very least, just like before we run the algorithm, we will have to build a priority queue. And we can build a priority queue by inserting all of the vertices, right? If we are denoting the number of vertices we have by V, then we can say that at each insertion, we will take log V runtime. So in total, inserting V nodes will take v times log v. The worst case scenario for Djikstra would be that we will have to travel or visit every node. And recall that by visiting every node, this also means that we'll be popping off all of the vertices in the priority queue. And once we pop off a vertex, we also have to update all of the connecting nodes, right? All of the connecting vertices. And the maximum, to update the value of a vertex, it would take log v time. And the total of times that we'll have to do an update would be equal to the total number of edges. Like how many edges we have, that just means that how many times we'll be doing an updating of the distance of a node. So this will be e times log v. The removal of a node will also take log v time. Can we have v nodes or like v vertices? So this would be just v times log v. Like to get the total runtime, we will just sum of these three multiplicative terms. However, we also know that the number of edges will always be larger than the number of vertices. So the three terms can be just simplified down to e times log v. Okay, now let's look over at A star. The worst case would be that for our A star algorithm, we have a very bad heuristic function that returns 0 at all vertices or at all nodes. Note that this is still like valid or like legit because it is admissible in the sense that the distance to go returned by the heuristics, it is still at least 0. And also it is consistent because it is not like the heuristics by returning 0, it is not larger than the true distance between nodes. So this bad heuristic function is trivially admissible and consistent. Also note that if all of the heuristics is just 0, then A star is just like Djikstra, right? So the runtime for Djikstra will be equal to the runtime of A star in the worst case, like A star with that heuristic function that returns 0 at all nodes. Yeah. Okay. For space requirements, recall that there are two data structures in our algorithms. Let's start with the priority queue. Like the function of the priority queue is just to hold all vertices. So if we have v vertices, then the space requirement will be theta v. On the other hand, the graph, assuming that we are representing the graph by using adjacency list, I've kind of like included a graphical draft of our adjacency list around here. So at this corner, we can see that the main list will have the length of the number of vertices that we have, which is like v. And the nested list, the number of entries across all of the nested lists, we just sum it up to all of the edges that we have. This works because like we don't have a cycle in the sense that we don't have two edges that is pointing towards each other between two nodes. So all of edges will only be represented once in our adjacency list, right? In that sense, we can just summarize or represent the number of edges that we have as E, and this is the number of entries in the nested list. So the space requirement for such adjacency list would just be theta v times E. And that's it. Thank you.